So welcome to this second video on longitudinal network analysis. And when I talk about longitudinal data, I'll usually talk about data like this, which we call ecological momentary assessment or experience sampling method, where we collect a lot of responses from a participant over time, using, for example, a smartphone app where the participant can fill in some questions per day on how they are feeling. For example, I'm sad, I'm tired, I'm nervous. And you might get multiple responses per participant per day, leading to quite a lot of responses overall if you do this for a few weeks, for example, per participant. Although another type of longitudinal data I'll also talk about later is data where we have a very large sample and we collect only a few observations and maybe then a lot of variables, which you might more typically see if you have panel designs where you have, for example, a panel of like 1,000 people and they all fill in a questionnaire. Then you probably don't use a smartphone, but the logic is the same because one observation comes before the other and the other observation comes before the next one, etc. Now, before I start talking about this, I wanted to talk about the reasons behind why you might want to estimate network models from longitudinal data. So far in the course, I think you have been analyzing mostly cross-sectional datasets. So why would you want to do this? Why would you want to look at longitudinal data rather than cross-sectional data? So you might want to pause video, for example, and think about this for a bit before I continue. Okay, so for me, there are mainly two reasons why I was interested in this. The first one is that using repeated measures of a person over time opens the door to estimating a network that is specific to that person. So as I said, many of the ideas to the network approach to psychology came from clinical psychology, psychopathology, where we were thinking about how symptoms relate to each other. And now this approach, of course, has been applied in many other fields as well. But especially in psychopathology, we might be interested in not large sample people, but we might be interested really in figuring out what is happening to this one person, right? This patient that we have in a clinical setting. And can we map out the structure of this patient's dynamics over time, for example? Well, if you want to have a model for one particular person, you're going to need a lot of data, and you can only get it from one person, so you're going to need repeated measures. The other reason is that many people have argued quite strongly against using cross-sectional data to look at or explore these type of relationships, because cross-sectional data doesn't necessarily allow you to study within-person dynamics. That is a pretty complicated topic, and I think it's very useful if you understand that. So I'll talk a lot about that in one of the next videos or a later part of the lecture. First, I'll talk about personalized network modeling in clinical practice. So if you collect data like this from a patient over time, where we have, for example, measures 4 times per day over a series of several days, the measures we will usually call beeps because the phone will beep. So at the beep, you fill in a questionnaire. Then the data might look a bit like this. So here we have a row. Now the rows in your data, they are no longer people because you only have one person in this case. We only measure data from one particular person. So every row is an observation at a different time point. Right, so maybe this was beep 1 time point day 1, beep 2 in day 1, beep 3 in day 1. So maybe that was like 9 o'clock, 1 o'clock, 5 o'clock. Okay, here we have 4 beeps, but let's say we have 3. And then here we have day 2. And then day 3, etc. The rest are just your responses to your items. So this data looks similar to what you had before, namely it's the data with rows being responses and columns being items. And we could actually just put it into BootNet and do the whole network stuff. But there's one thing we need to take into account when we have this type of data, and that is that we now know that this row comes before that one. And that one comes before that one. So that there's also some overlap across rows or across time. And we need to handle that statistically. That's a whole statistical argument for that. You need to assume your rows are independent, otherwise your likelihood is not computed correctly. Not that important, but statistically it is important. But also practically it might be something that we're interested in, because we might want to see if we can explore things that predict each other over time, which would be very useful, especially if we're looking in potential causal pathways. And I'm not saying these arrows indicate causal effects necessarily, but there are other interpretations as well. But if you're exploring potential causal pathways, it would help if you have something that goes over time, because usually causation doesn't go backward in time. Actually, unless you have like the Avengers going back in time, and then there's a whole multiverse thing, and it gets complicated. So maybe we can just assume that causation goes forward in time. So this is your data, and the way that we analyze this data and the type of networks that we estimate from this data, we usually call vector autoregressive model or graphical vector autoregressive models. Now what's happening here in this graphical vector autoregressive models, we actually don't get one network, but we get two. So we get a contemporaneous network and a temporal network. And this contemporaneous network, this is actually the Gaussian graphical model or the partial correlation network that you've already seen before. So we add this temporal fact structure, which tells us something about how do variables relate to one another over time. So in this temporal network, an arrow here indicates that a change in A predicts a change in B over time. And with a change, I mean a change from the person-wise mean. So that means that if my response on variable A is higher at some time point, I predict than my average, I predict that my response on variable B will be higher at the next time point than my average. And that relates to these arrows here in the dataset. So you might see there's no arrow from the last measurement of the day to the first measurement of the next day. So we have to do it within day. And if this arrow is here, it simply tells me, okay, there's some predictive effect here over time. In the contemporaneous network, we take these temporal effects into account. So here A is actually a latent cause on B and C, so we need to take it into account so we don't get some effect between B and C just by having an A as a temporal predictor. So we control for that, and then we get the partial correlation structure that we know, and that tells us something about how the two variables relate to each other in the same window of measurement. Right, so here we don't cross nights, so we can just use all observations. So this arrow here tells me, okay, if I score higher than my average on variable B at some time point, I tend to score higher than my average on variable C as well, if this is a positive effect. So those are two different things: temporal prediction over time and contemporaneous prediction at the same time. And again, here, when I say at the same time, I mean in the same window of measurement. So usually these questions are like, in the past 2 hours, did you experience this? Or in a panel data set, you might ask, on average, do you feel this lately or not? You're not really asking about this specific moment, because you can argue, okay, can this be indicative of a causal effect? Well, if it's really a true contemporaneous effects between things that happen at the same moment, then okay, causation can't really be exactly instantaneous. But if it's about something that happens within the same window of measurement, then it can be indicative of something causal. It's simply something that does faster than whatever window of time we have here. Right, so maybe we measure people, let's say if we did here, 9, 10, 11, 12, 1, so 4-hour time differences. And maybe there are some effects that are simply faster than that, like faster than that 4-hour window. Those we can then capture in this contemporaneous network. I'll talk a bit more about that later as well. So this is what it looks like in practice. This is a network structure that is estimated from a patient in a clinical setting, where we administered a small questionnaire for several weeks on this patient, and the patient filled in. Then we can estimate these network structures afterwards using graphical vector autoregressive techniques. The way this model is estimated used graphical var package, and the method is actually very similar to the EBC GLASU, in that it used regularization together with extended BIC model selection. It's similar than what you saw at the cross-sectional network analysis. And usually the logic, the ways which you can estimate models, it transfers to these type of models as well. So that's one way to do it. You can also use model selection or thresholding, other ways to get a similar network structure. In this NS1 modeling as personalized network modeling, we usually prefer to use lasso regularization because we just have very little data to work with. So then that works best. So we get two network structures, a temporal network and a contemporaneous network. So what does this mean? Here, for example, we see body discomfort with the blue arrow pointing to nervous. That means that whenever she, in this case, experienced more body discomfort than her average, 3 hours later, I think it was 3, the lag interval in the study, she was on average more nervous than she was normally. This arrow here means that if she is tired at one time point, on average she was also tired at the next time point, which kind of makes sense because you're usually tired for like a whole day, right? So that's what we call an autoregressive effect. At the contemporaneous level, we see that this relaxed variable played a very important role. Whenever this person was feeling relaxed, that person experienced less sadness, was less tired, experienced less body discomfort, and concentrated better on average. And yeah, what can you do with a model like that in clinical practice? Well, this tells a story. Of course, it doesn't really replace a therapist. We're still working with an estimation here. We might be wrong on some edges. We might have not enough power to detect some edges. But it is a useful tool in clinical practice that the clinician could use in addition to other things to talk with the patient. To talk with the patient, okay, this is what your network shows. Do you recognize yourself in it? Do you think that relax indeed plays such an important role here? Which might be useful for the patient to get that level of insight in their lives. In addition, of course, if you're going to gather this data, and there have been some pilot studies now that do this in clinical practice, that start to collect data and try to estimate a network and use it in clinical practice, and it seems that patients really like this level of feedback. But in addition, you can also just look at this data by itself. It's very valuable data to look at. So here, for example, this plot of the time series of the different variables in this network, being angry for a different patient, and you can see, okay, this is how you experience anger over time. So on November 10 in the afternoon, you're very angry, right? So that might be useful for the therapist to know. It seems here that there's maybe a bit of a cycle even in these spikes of anger. So that could be very useful for a clinician to guide the conversation, of course. So I think gathering this type of data is very valuable in clinical practice because we can do this kind of stuff, right? But we can also do more. We can do quite a lot of quantitative analysis with this type of data. So we will probably see this type of data also more often in the future. Now this is nice. And I wrote some papers about this, about how you can use this in clinical practice, about these ideas. But then one thing I was worried about is, okay, this looks nice, and if we simulate it, it kind of works, but is it actually feasible to do this? Can we estimate these type of networks in clinical settings? And I was a bit worried about that. I still am. Because if we compare this type of NS1 network, the graphical var network, to what we use in cross-sectional data, we might see that it's just much more complicated than what we do in cross-sectional data, right? So here we see two networks. We add all these potential temporal effects. So that means that the networks that we estimate from time series data are just more complex, include more parameters than the network that we estimate from cross-sectional data. Right? So for example, if you have a 10-node network, in cross-sectional data, we would have 55 parameters, 45 network edges, and 10 variances or scaling parameters, or whatever you want to call it. In the Gaussian graphical model, we would have 100 more parameters because we need 100 potential autoregressive or cross-select effects. So that makes the model much more complicated. At the same time, we have some assumptions we need to make. I didn't talk about them yet, but we need to assume that people don't change over time, otherwise we can't estimate one model for a person. We need to assume that our measurements are equally distant from each other, so we don't have a gap of like 6 hours and a gap of 4 hours, for example. Otherwise, the interpretation of the parameters is harder. So we have some assumptions that are questionable, and we have a much lower effective sample size. And with that, I mean that in cross-sectional network, we see data sets of like n is 500 to n is 1000 is not uncommon. And if we run simulations, Adela added a paper on simulation studies, for example, which showed that for cross-sectional networks, you need quite a lot of observations to get really reliable results. In NS1 studies, we can't get 500 observations of a single person. We can maybe get at most 50 to 100. So we have less data to work with. And even if we can get 500 observations, then maybe we are gathering data over such a long time frame that the person is no longer stationary. In addition, so let's say we have 50 to 100 observations. In addition, the effective sample size is even lower. And that's a bit weird, but we have to realize that there is an autocorrelation between consecutive observations. It means that my score at 9 o'clock is correlated with my score at 12 o'clock. What does that mean? If that correlation is 1, then it means my score at 9 o'clock is the same as my score at 12 o'clock, is the same as my score as at 4 o'clock, is the same as my score later. And all my responses will be exactly the same. In that case, even if I give you 50 responses, but I answer with a 4 50 times, effectively you only have one response, namely you have my 4, and that's just repeated 50 times. Only if you have an autocorrelation of 0, so there's no temporal effects, would we effectively have exactly the same sample size and the number of observations. So here I have 5 responses. Effectively here we have 5 responses, but here we only have 1 because you only have that 4. There's a bit of a gray area between when you go from that 1 response to that 5 response. So if you have some autocorrelation, there is an overlap in information, so maybe effectively you only have like NS3, NS4 in this case. Right? So that's quite problematic. We need more parameters and we have effectively much less sample size. So is it feasible to estimate these network models from clinical datasets? I did a study on this, and we published that where we took some networks that we simulated under, and these networks are based on large sample studies I'll talk about later. They might be similar to what we can expect to find in clinical practice, although they're not really based on patients. So if you simulate on a different network structure, you get different results here, of course. But if you simulate under this, what we get is, if you have here the number of time points, here we see the graph, and this one was the most interesting one, sensitivity, which simply means the power to detect edges, so the probability that you're going to find an edge in the network. Only at 500 time points it started to be quite high. Before that it was quite low. It's a more reasonable time points that we might expect to have in clinical practice. What does that mean? It doesn't mean that we cannot estimate a network, but it means that we might miss edges. So maybe, okay, this is the network that we have, but maybe we missed some small effects here that should have been included simply because we did not have enough power. That's important to know if you do this type of modeling in clinical practice, that you have this power problem. You have limited power to detect edges. And yeah, how do you solve that? Really, the only way in an NS1 setting to do that is just by limiting the model as much as you can. So we can't do this for 10, 20 nodes in an NS1 personalized setting. We can do it maybe for 5 nodes or 6 nodes. But that can still be informative in a clinical setting. Now, another thing that we looked at is seeing if we can improve this estimation accuracy and improve how well we can estimate these models by incorporating prior knowledge or clinical expertise in the network. And this is something that's quite interesting in this type of personalized network modeling in clinical practice. That other than many other fields that do network analysis, this is based on a person, and we can actually ask that person questions. And we have also clinical expertise and clinical theories. So before we collect the data, we might already know quite a lot about what potential relationships we might find. And this might be beneficial in estimating the network. So this is something that Julian Berger, a PhD student of mine in the Netherlands, developed, called PREMIS, the Prior Elicitation Module for Ideographic System and Estimation. And what we propose here is to include expertise in the estimation using a Bayesian framework. This is a very complicated figure, so you don't have to really look at it in detail. The main thing I want to show is that the main method in which we now estimate networks, in which you have been doing it so far, is what I like to call agnostic, which means that we don't make any prior, we don't have any prior belief on what the network should be. And if we do that, we're simply trying to find evidence for an edge being there. So our null model is a network where there are no edges. We try to find evidence that an edge is there. And then if you have enough evidence, for example, an edge is significant or it survives lasso thresholding, we include it. But in clinical practice, we have a prior idea. We have clinical expertise. We can ask the patient questions like, what do you think is going to happen? So we could also take a starting point, not this basic null model where nothing is included, but a clinical expertise model that includes already things that we expect to be in there, and then try to find evidence in favor or against that model. This might help estimating these models if we have a really strong prior idea already on what the network would look like. If you're interested in this, then check out this paper. It has some really nice figures as well, explaining network modeling. So there are some challenges to personalized network modeling. It's not that we can always do it, but it's very promising, but it's not without concerns. So it might be hard to get sufficient sample sizes in this purely ideographic NS1 setting, so really where we have only data of one person. Using prior information might help, but then we need to find this prior information somewhere. We need to get an idea of where do we get the prior information from. And another thing that I will talk about in the next video is that if you have only information on one person, of course, we cannot study how people differ, because we cannot look at how people differ if we don't have multiple people. So one solution, and I'll put solution in brackets because some people will disagree that this is a solution, is to, instead of looking at NS1 studies, investigate these rich data sets where we have multiple observations of multiple people. So we have NS more than one time series data, and we have repeated measures also of many people. If we do that, we can estimate a model that is common across people, or maybe a model for the average person, and use that as prior information or to guide your clinical practice, or simply to uncover what's happening within and between people in a set of variables. So that's what I'll talk about in the next video.